Hi everyone, in this video we are going to discuss about the necessary condition for exactly one root of a quadratic equation to be between two real numbers. Say for example we have a quadratic equation ax squared plus bx plus c equals 0, and then what would be the necessary condition for one of its roots to be between two real numbers, let's say k sub 1 and k sub 2. So here I have noted that either alpha has to be in between k sub 1 and k sub 2, or the second root, which is beta has to be between k sub 1 and k sub 2. I have already created videos on 4 other situations, and this is the 5th situation where we are going to try and understand what would be the necessary condition for exactly one root of a quadratic equation to be between two real numbers. Here I have diagrams for the quadratic function when the leading coefficient is positive. Now let's first try to find out what would be the condition using these two diagrams. I have two other diagrams down below for the leading coefficient being negative. So now let's use these diagrams and try to understand what could be that condition. Now if exactly one root has to be between two real numbers, then can we say it like this? Let's look at the first diagram, and here I am going to plot k sub 1 and k sub 2 on the positive x-axis in between the first root, and then in the second diagram I will plot it in between the second root. So here in the first diagram I am going to plot k sub 1 and k sub 2 in such a way that the first root will be between k sub 1 and k sub 2, and in the second diagram I am going to again plot k sub 1 and k sub 2 such that the second root will be between those two real numbers. So in both the diagrams I have plotted the 2 points k sub 1 and k sub 2 in such a way that exactly one root is between them, right? Now at those points, if you think about the value of the function, or rather the nature of the value of the function, in the first diagram you can see that at k sub 1 the function value, which is f of k sub 1, that is looking like positive, and the function value at k sub 2 is looking like negative, which is actually f of k sub 2, that is looking like negative. And similarly in the second diagram also, if you see that the function value at k sub 1 is looking like negative and the function value at k sub 2 is looking like positive. So now if we take a product of these two values, I mean the product of the function value, so we can say f of k sub 1 times f of k sub 2, this product is actually looking like negative. Whether alpha is between the two numbers or beta is between the two numbers, in any case the product of the two function values at those 2 points is looking like negative. So this is the only condition we need for exactly one root to be between k sub 1 and k sub 2. We really don't need to consider the discriminant, because in this way we can guarantee that the parabola cuts the x-axis, because when the leading coefficient is positive and the function value is negative at a point, that is possible only when the parabola has already cut the x-axis and a point is actually on the x-axis within the parabola. That is when the function value could become negative. Otherwise, when the leading coefficient is positive, then the function value can never be negative other than this one exact situation, right? So this one condition will guarantee two things. It will guarantee that yes, the quadratic equation has two real roots, and also it will guarantee that exactly one root is between k sub 1 and k sub 2. Now let's also quickly take a look at the function graph when the leading coefficient is negative. The second set of diagrams are actually when the leading coefficient is negative, and for those two parabola again I have plotted the 2 points k sub 1 and k sub 2 on the positive x-axis, and there you see that the function value at k sub 1 is looking like negative. In the first diagram, of course, the function value at k sub 1 is looking like negative, and the function value at k sub 2 is looking like positive. And if you look at the second diagram, there the function value at k sub 1 is looking like positive, and the function value at k sub 2 is looking like negative. So whether k sub 1 and k sub 2 is located as in the first diagram or as in the second diagram, you see the product of the function values at those 2 points will be negative. So the point that we have already noted up above, that f of k sub 1 times f of k sub 2, this product will be negative. It is true whether the leading coefficient is positive or negative. It will be true only in this situation, right, when exactly one root is between the two real numbers k sub 1 and k sub 2. And that is the only necessary condition, and that is the sufficient condition to make sure that exactly one root of this quadratic equation will be between k sub 1 and k sub 2. Let's take an example. Let's suppose we have an example like this: x squared plus p minus 5 times x minus 5 times p equals 0. That's a quadratic equation. And the question here is that for what values of p, one root of this equation will be in the range 1 to 4, between 1 and 4. Here I am using the interval notation. This is actually not a coordinate. This is actually the interval, right? Interval between 1 and 4, both excluded, of course. That means exactly one root of this quadratic equation will be between positive 1 and positive 4, and for what values of p. So we have to find out the values of p for which exactly one root of this quadratic equation will be between positive 1 and positive 4. So let's try to solve the problem. Now what is our necessary condition? Our necessary condition is like this: f of k sub 1 times f of k sub 2 has to be less than 0, has to be negative. This product has to be negative. Now in this case, what is k sub 1? Well, k sub 1 is actually right here. This is actually k sub 1, which is positive 1, and then positive 4 is actually k sub 2. And what is our function here? Well, our function here, we can make a quick note that our function would be, we can say, well, then definitely f of x is equal to x squared plus p minus 5 times x minus 5 times p. So then f of k sub 1 will be actually f of 1. So from here we can say, well, then the product will be f of 1, because k sub 1 is actually 1, as I have indicated right there, and f of k sub 2 would be actually f of 4, and this product has to be negative. So what would be f of 1? Well, I'm going to use a bracket here, so we can say f of 1 would be 1 squared plus p minus 5 times 1 minus 5 times p. I'm just substituting 1 for x. Wherever we had x, I have replaced x by 1. So that is f of 1 times, so what is f of 4? Well, f of 4 would be 4 squared plus p minus 5 times 4 minus 5 times p, and this product has to be less than 0. Now from here, what do we get? Let's simplify further. So here within the first bracket we have 1 plus p minus 5 minus 5 times p, and then in the second bracket we have 16 plus 4 times p minus 20 minus 5 times p. This is less than 0. And then from here, what can we say? Well, in the first bracket we have negative 4 times p and negative 4. So that would be, we can write it like this: negative 4 times p and negative 4. And then in the second bracket we have negative 4 and negative p, so that would be negative p and negative 4, so negative p minus 4. This product will be less than 0. And from here, if we take out negative 4 from the first factor, so we can say, well, then negative 4 times positive p plus 1. And then from the second factor, let's take out negative 1. Then we are going to be left with positive p plus 4, and this product is less than 0. And from here, what do we get? Well, if we multiply the negative 4 and the negative 1, they will give us positive 4. And then if we divide both sides of this inequality by positive 4, then on the left hand side, we are going to have p plus 1 times p plus 4, and then on the right hand side it would be 0 divided by 4, so that would be 0 anyways. And to find the solution set for this inequality, let's quickly use the wavy curve method. So I'm going to draw the real number line here. From the first factor, what is the critical point? Well, the critical point would be p plus 1 equals 0, that means p equals negative 1. So negative 1 is a critical point. So let me plot the negative 1 here. Let's suppose this is our negative 1 right here. And then from the second factor, our critical point would be p equals negative 4. So let's assume that this is where we have negative 4. So then let's draw the wavy curve. On the right hand side of the highest critical point, everything is positive, meaning the function value would be positive, the expression will be positive. So here this is the positive side, and then between 1 and 4, obviously the expression will be negative, because the multiplicity of the factor that gave us this critical point, which is p plus 1, that factor's multiplicity is 1 because its exponent is 1. So on the left hand side of negative 1, the value of the expression will be negative. And now let's see what happens when we go to the left hand side of negative 4. Well, negative 4 is a critical point that came from the factor which is p plus 4, and that factor also has a multiplicity of 1, meaning its exponent is 1. So when you go to the left hand side, the sign will change again. So then the value of the expression will become positive again. So I'm going to draw it like this. And now if we denote that with the sign, so this would be positive zone, and this is the negative zone, and this is the positive zone. So the value of this expression is negative between negative 4 and negative 1, right? So then what would be the solution here? Well, the solution would be, we can say, well, therefore p will belong to the range negative 4 to negative 1. Now can we include negative 4 and negative 1? Of course not, because it's a strictly negative condition, meaning you see the two factors there, their product is actually less than 0. They are not less than or equal 0. They are strictly less than 0. That means we have to take only the pure negative zone. If we take the negative 4 or negative 1 in the solution set, then guess what? The expression value will become 0 at those 2 points, and we don't want that, right? It has to be strictly less than 0. So we have to exclude the true critical points. So then P has to belong to a range of real numbers like this, for which the quadratic equation in this example will have exactly one of its roots between 1 and 4. I hope everything made sense. Thank you for watching. See you in the next video.